Hey, Vlad here, devinside.com. Welcome to another video. In the previous video, we basically revamped our design again, and we started to use for each to implement the most important methods on sets. And today we're going to continue with that, and we're going to finally start dipping our toes into generics, but we will realize very quickly that we actually can't do that, and we have to jump in head first. Let's get started. Alright, so this is where we left off, and let me start SPT. So we're again in the Ubuntu virtual machine, and we have Sublime at the top and SPT at the bottom, which is running in a regular terminal as always. So the first thing that we're going to do is we're going to move those var args tests a little bit to the top, because the tests that are before are testing for each, and we're going to keep working on for each and on the other things that built on top of that. So I just want to keep writing tests at the bottom, right? So this is the first test for each, and I'm just going to paste those in, and Scalariform is going to refactor everything. All right, so today's video is going to start with the realization that there's something magical happening over here, right? So actually, what this line is doing is it calculates the result of function element, which is unit, right? And over here we have a other elements result, which is also unit, right? And then they're basically getting thrown out, right? Because unit, it's not a very valuable type, no pun intended. This basically means that we can pretty much ignore the result type, right? The values of the result are being ignored, and therefore maybe we can also ignore the type of the result, right? So essentially, what I'm trying to do is I'm trying to implement the following test. By the way, if I save this, everything still should be fine. I'm trying to implement the following test. I want to say that for each should be parameterized in the result of the argument function, right? So what do I mean by that? I mean by that if I have an empty set, right, and if I call for each, then it shouldn't matter the value of which type I'm producing it, right? So over here, for example, this is an integer, right? Whatever this function is producing is this result over here, right? And it's getting thrown out anyway. So why shouldn't it be possible to pass this? Let's see what's going to happen. All right, we get some warning, but the test passed. Let's check out the warning. So the warning is saying a pure expression does nothing in statement position, right? So basically, what is happening over here is that there's some magical thing that converts an integer to a unit. Remember, we had this from the very beginning, right? So if we had some sort of scope over here, right, and we had some value, right, and then if we would have a print line over here, let me scroll down a little bit. No, actually, that's the wrong example. This is not what I wanted to show you. I want to show that if you have a scope, right, and you say val x, and this x is of type unit, then you can give it an integer, right? So you can do, I don't know, print line, whatever you want here. And then you can give it an integer, and it will still compile. Let me actually move it inside of the class, because I can just start doing something like this, outside, right? So there's some magic there. So see, we're getting exactly the same warning. Hold on, let me scroll up over here. My face is covering that up, so it gives us exactly the same warning. A pure expression does nothing in statement position. The same as over here. A pure expression does nothing in statement position. So basically, there's something built into the compiler that can convert any type, like a value of any type, into a unit, which is arguably a bad thing. But it makes it also has a value, right? So basically, this is sort of happening by coincidence, right? And the proper way to do that would be to implement multiple versions for each, right? So there will be one version that takes a function from string to unit. There will be another function that takes a string and produces an int, and there will be another function that takes a string and produces some other type, right? So basically, there's this infinite amount of overloads that we would need to write, and parameterization of types, or type parameterization, is exactly there to solve this problem. So what we can do, and we have seen it over here, like for example, this is exactly what is happening over here. Or every time we have an option of string or an option of int, or even if we have the main method, right, we say there will be an array of strings, right? So we're finally arriving at the point where we can declare methods that use that, right? And this is how the syntax works. So you have a def over here. And after the name and before the parameter list, you can just define with rectangular brackets whatever you want. So you can give it any name you want. Usually, just capital letters are used. Like usually it's T or E. T for type or E for element or something like this, right? Over here, I'm gonna say result, right? So basically, this function can produce any result that it wants, right? And the cool thing is that the compiler will actually infer this type, right? So every time we're saying for each, for example, over here, right, the result is actually going to be an integer, right? But we don't have to specify that. Scala is able to infer that type, okay? But the syntax is the same, basically. After the method name, before the parameter list, same over here, right? The declaration side and the call side, okay? Let me remove that. Okay, so now no warning is being produced. And now let me actually also remove that. And that over here, like that, and now it's exactly like it was in the beginning, and it still works. Now that we dipped our toes into the waters of generics, and we haven't really I haven't really explained exactly what it means to program in this way. Let's just try to keep going and see how far we can get with this. It turns out that we can't actually get too far. And by the way, this test should actually say so that it does not produce warnings, right? Unfortunately, I have Googled this a little bit, and I don't know of any way to use any testing framework. Actually, I Googled only for Scala tests, so I just want to be speaking for Scala tests. I don't know if it is possible. I believe it's not to make sure in the test that no warning is being produced. I believe that this is not possible. Anyway, the next test we're going to write is going to be written for a function that is called map, and the signature for the map is going to look very much similar to for each. In fact, I really want it to fit into one line, so I'm going to do something like this, right? So this is the signature for each, and what I want to have is I want to have another function called map, right? And map will have exactly the same signature, but in the very end, it will actually produce a new set, right? So it's going to look like this. And as of right now, let's just throw an exception, okay? So the test that we want to implement is basically exactly the same as for each. Let's go to for each, the very first one, for each. It is this one. For each on an empty set should not apply the function. Let's actually just copy that. Copy that, go down over here, like this. Let's call this map, and this one map, right? Let's actually, I'm gonna swipe it left and right from time to time so that you kind of see it, so you can read it better. I actually don't like this this wrapping, but this outer wrapping, but I want you to see everything, right? For example, this, like it's really hard to read this. Okay, so now it obviously fails because of this, right? It's easy to fix. We don't need the proper implementation to fix this. We just need something that will fix exactly this case, right? So we can do if is empty, and then just produce an empty set, right? Which is basically, you can just say this, because if this is empty, then we can just return this, and otherwise we can keep throwing the exception just for now until we have actually the test that, the test this branch. All right, so let's add a test that is actually, more interesting, right? So let's say a map on an, actually, let's just say map should produce a set, right? We actually don't really care what's going to be in the set, right? So let's just have a set, and usually we use random strings, but this time I'm going to use hello and world, and I'm going to map them, right? And map wants a function that will take the string and produce a result. And in the beginning, I'm going to make sure that the result is also going to be the string. So actually, I'm going to remove that, just for now. So it's going to be a function that takes a string and produces another string, right? So over here, we're going to say reverse, right? So basically, it will produce another set, which should be set off. And now we just need to manually reverse hello and world. And actually, I'm also going to swap the order, because remember, the order in the set doesn't really matter, right? So let's reverse the world. It's going to be DLROW, right? World. And let's reverse hello, which is going to be ole. All right. So let's see if that actually works. It shouldn't work, because we're actually just throwing an exception over here, right? So the way we solve this is basically the same way as we do it over here. So what we do is we copy that, put that over here, right? And don't forget the braces. I don't like the braces, but they are necessary. Okay, like that. Okay, and what we need to do here is we just need to say not empty. We apply the function to the element, and then we just do the same thing for the other elements. Dot map function, right? So it's very, very similar, right? So see, we have the same thing as over here, and we have the same thing as over here, but instead of for each, we're saying map, right? So it's going to be like this. And before we were doing basically the same thing, right? For every method, we would do this manual recursion, but now we actually have for each. Then why not use it, right? Why not use for each? So instead of all of that, let me comment this out for now. Let me just use for each, right? So for each, every time it starts with some result, it's going to be equal to something. In the end, we're going to return the result, right? Let me scroll down a little bit. And over here, as always, you're going to call for each, right? We're going to have a current, and we're going to do something to the current. Probably we're going to do something like result equals, right? So this is the the common structure for each. So we're going to start over here with an empty set, right? So because we need to return an empty, we need to return a set, so we need to build a set. And how do we build a set? Well, we start with an empty set, okay? And then over here we say result equals result.add, and for each, look. And for each, we're basically just applying the function to the element. So we're going to do the same thing over here, right? So we're just going to do a function current, and this is already map, right? So we're just walking through every element, and we're just producing another set based on that, while applying this function, right? So in for each, we actually didn't have to rebuild an entire set, right? Because we were just like throwing out the results of this operation. But in this case, we actually need that. Right, so let's throw this out. So now we have map. So we have for each and we have map. And now we have the same question as we had for each. Why shouldn't we be able to produce something else over here, right? Let's try that. So let's try the test first, right? Let's try the test over here. Map should be able to produce a set of something else other than string. Because why not, right? Let's say something very, very simple. Let's say set of hello, and we keep saying world. Let's say planet. Hello planet. All right, hello planet. Okay. So now I want to be able to map each element to its size, right? So this should be a 5 and this should be a 6, right? Or length. String has a method called length or size, right? So this should be a set of 5 and 6. And by the way, I didn't use hello world. Let me show it to you like this, right? By the way, if I save that, then Scalariform will add a space over here, right? So right now it's failing because it says, hey, type mismatch. It doesn't even compile, right? I didn't use world because I didn't want to confuse you. Because if we do hello world map dot size, this should be a set of 5 and 5, and a set of a 5 and 5 is just a 5, right? But I really want to, I'm guessing this is the one of the very first times that you've seen something like map, and what map is doing is it applies a function to each and every element, the same as for each. It's just that it doesn't throw out the result. It builds another set while it does it, right? So for now let's leave both of them there. It doesn't compile right now, right? So let's try to fix that. And it turns out that it's not going to be so easy to fix as it was for each, right? So let's start the same way. So we have the result over here, and we have the result over here, and now we have a problem. Now we have a problem that it says, okay, so found the result required string. So basically this function, right? So now it doesn't produce a string anymore, it produces a result. But add, it wants a string, right? Because we only have sets of strings. So basically, if we're not building a set of strings here, then we have to copy paste everything that we have and create another set that works with integers, and create another set that works with dogs, and so on and so on. We already know the solution to that, which is parameterization, type parameterization. But now it will actually cause us like so many problems, which we will fix right now. So the same way as you add a type parameter to a method, the same way you can add the type parameter to the class or a trait. So by the end, when we will be done, this will not produce a set, this will produce a set of result, right? And this, it will not just be an empty set, it will be an empty set of result, right? And add, it will be parameterized, basically parameterized. The parameter is not going to be here, it's going to be somewhere else, but basically it will allow us to pass in whatever we want, not whatever we want, but basically it will make sure that in this case add wants a result, because the parameter will be sort of inside of this. Let's just start doing it and then it will become clear. Okay, so the same way you can add a type parameter to a method, the same way you can add it to a class or a trait. So if you go to the top Over here we have a set. The same way, like after the name and before everything else, you can add a parameter, and this parameter is going to be called element. Okay, and it's going to extend a function that takes an element and produces a boolean. Right. So basically, everywhere we say string, now we have to use element. Okay. Before we do that, let me actually go down. Before the whole mayhem is going to start. Let's go to non-empty and make sure that it also takes a parameter element, right? And it extends set of this element, right? And this means that the elements are actually going to be of type element, and other elements are also going to be set of this element, right? And the same thing for non-empty. We can't have a generic parameter. We can't have a type parameter for an object, right? So this has to become a class because we're not creating objects ourselves. Like, the objects are sort of being created for us by the Scala compiler, right? So this needs to become a class. And it can become a case class because a case class is they require at least one parameter, so it has to become a regular class, which doesn't really matter because it's private and whatever, right? So it's going to be an element over here, right? And now at the very bottom over here, val empty cannot be a val anymore. It has to be a def. It has to be a def, which is also parameterized with some element, right? And it will produce a set of some element, and it will basically create a new empty, right? Because it's not a case class anymore. We have to use the new keyword, and we have to pass in the parameter over here, new element, right? So if I try to compile this now, we're gonna get like gazillions of compiler errors. So I'm just gonna keep going like from top to bottom and try to fix like everything that I can find. And as soon as I'm under the impression that I found all of them, we're gonna try to compile. In fact, I didn't save the file yet, so you know what we should do? Let's just switch to compiling, and compiling means not running the test, and also it means not compiling the test, right? So we're going to do it step by step. We're going to try to compile the code. Okay, so 150, we can pretty much ignore it because this is the map that is still, it's still not ready, okay? Because I didn't save the file, okay? So let's go through everything. So apply is not going to get a string, it's going to get an element. Let's see over here, that should be fine. Add, you can add any element you want now. And over here, it's going to be a set of element. And over here, it's also going to be an element. And this is going to become a set of element. And let me see, all of that is fine. Okay, that is going to be an element. Set of element. Set of element. Let's see. Set of element. Set of element. Difference, same thing. Nope, not empty. Oh, come on, element. There we go. I can just say, I can just say capital E and then tab, and it will autocomplete for me. That's fine. That's fine. A subset of set of element. Let's see. That's all fine. Set of element. Over here, we need to be careful. Like usually there is a problem with type erasure, but in this case, Scala understands that we're forced to specify this type, so it's fine in this case. What else? Hashcode should be fine. Oh, here, the same thing. It should be a non-empty of element. What else? That's fine. Size should be fine. Is empty. Oh, this is very important. So this thing alone, actually, I'm gonna leave this, and I'm gonna say to do fix me, because remember set.empty, this is not actually it should be just empty, right? This is not a val anymore, which was just returning an object. So we're comparing to instances, like multiple instances of the same class now. So this will fail. In fact, once everything compiles, we're gonna see, like, I don't know, a bunch of errors just because of this, and we'll come back and we'll fix that. Let's keep going. Okay, so non-empty of element, and let's go down, non-empty of element. Let's see. Oh, this is not a string anymore, right? This is element. For each, the same thing, element, non-empty element. Now it feels like, it requires a lot of typing, but think about what it buys for us, right? Which I still haven't explained yet. I will once I fix the errors. All right, so let's see. Result, same thing. This is going to be an element. What else? Okay, this should also work. This is going to be an element, and the element should come in over here. You know what? I'm gonna call this E just so that you see the difference between, because we're not in the we're not in the class anymore. So this is its own element. Okay, so element, and it's gonna produce a set of elements. So over here we're gonna have an empty of element, add element. What else? So this is gonna be a set of element then. And by the way, maybe Scala inference is going to help us out, and we will not need to do this, right? Because remember, an empty now is a def that is parameterized. Okay, so let's keep going. This should be fine. We have it over here, right? That's fine. Over here. All right, so I don't want to do this over here, so we're just going to say that it produces an any, because, right, remember, these are the pattern matches that we disabled. So basically, it doesn't really matter what we write there because we don't want anything related to that to compile. Okay, so let's see if I missed something. And of course, I did 15 errors, right? It says private object empty extend set. For example, over here, I missed to say that. Oh, where did I convert this thing to a class? Oh, I converted the wrong one. All right, so this is still an object, not empty. Okay. Right, and this one should become a class. Empty, right? Element comes in, and it gets delegated to this one over here. Right? Okay, let's see. All right, only 6, which is good. Let's see the first one. The first one's happening on line 32. Let's see, 32. All right, so this is like one of those cases where we need to help the type inference a little bit. So over here we can say that this is an empty of an element. Right, so now we have only 4 errors left. It's probably the same thing somewhere else. Let's see, 53, which is over here. Yeah, it's pretty much the same thing. So we're going to do element over here. We're going to do element over here. Maybe it's going to be enough already, actually. Oh, yeah, it is actually enough. Okay, so now let's try to run the test, and the tests themselves are also not going to compile. Right, because now every time we say empty, we also need to provide the type parameter, this one over here, right? Okay, so let me do that. Let me go to the top over here. All right, so let me see the first one. All right, 103. 103. Okay, it's this one. It says that empty set something something nothing something string. Every time you see nothing, it means that the type inference needs some help, right? So over here we were working with strings, right? So let's do that. 11 errors. All right, so let's scroll up again. It's kind of unfortunate that we have to scroll up. I mean, we could have started with the last one, but let's just keep going like this. 136, probably the same thing. Yeah, it's the same thing. Over here we need to say that it's a string. 7 errors. It's fine. All right, 169. Okay, so Control G, 169, enter. Same thing over here. String. Because so far we have been only dealing with strings, right? Okay, only 3 errors left. It's 329. 329. Okay, it's the same thing. So if we knew that this was an empty set of strings, for example, right, then we wouldn't have this issue. 387. 387. Same thing here. Set empty string, and the last one is 391, which is over here. Same thing. Okay, right. So now everything should compile, but it still should fail because of this reference thing. Remember, look at how many tests it's gonna break. 47 tests, right? This is usually a sign that either something with the test is wrong, or there's some very central, very important point crucial point that is broken, and it is this one, right? So it's this empty. It is empty. We just need to say this is instance of empty. Yeah, empty element, and that's it. That should fix all our tests. Yes, there we go. They agree. All right, so let's talk about what just happened, right? Because our tests were, this is the first time that it sort of happened that our tests were not passing for like very, very long time, right? I remember the first time when we changed the implementation completely, we had this old set and new set, and we were able to gradually keep going like this. Well, in this case, we were doing something with the compiler, and the compiler can't do things incrementally. It has to do everything basically at once. So either the thing compiles or it doesn't, right? So what is type parameterization? Type parameterization is a type. It's a type. It is a kind of polymorphism. There are basically only two. I could say kind, but let's say axes or dimensions. There are only two of them that are known to, well, me. I would say that I was about to say that there are only two of them known to computer scientists, but I'm not gonna pretend like I know everything. So there are only two of them are known to me. The first one is the type parameterization, as you have just seen, right? So this is a polymorphic way of describing types, right? Actually, forget that I just said that. Okay, so there is type polymorphism, and there is ad hoc polymorphism, and there are two kinds of ad hoc polymorphism. The one we already know, which is subtype polymorphism. And the other one is type class polymorphism, the one that we haven't talked about yet. We will though, right? So what's up with this ad hoc thing? Why is it called ad hoc? Because so far we have always been calling it subtype polymorphism. Well, ad hoc means that at some point, it doesn't really matter if it happens at compile time or if it happens at runtime. In case of subtype polymorphism, it actually happens at runtime. One form will be chosen, and then based on that form, the behavior will change. And for the type parameterization, it's sort of the other way around. It's diametrically opposed. It doesn't matter which type you choose and when you choose it, the behavior will be the same. I remember this example with, I'm not going to go to my example with, with electrical devices and whatever. The typical example is, to have an animal and to have a dog and to have a cat. And when you say, animal, when you call like make sound on an animal, then it will be, the implementation will be chosen ad hoc, right? So if it's a dog, then it's going to bark. If it's a cat, then it's going to, meow and so on, right? Whereas with type polymorphism, it's the other way around. So for example, we have a set of strings, and we have a set of int, right? It's different forms, right? But every time we say size, the behavior is going to be the same, right? It doesn't matter if it's strings or int, right? So ad hoc polymorphism is there to change the behavior, right, on the fly, and the type polymorphism is there to keep the behavior, right? So it's basically to make more things compile, which is kind of cool. Also, there are many other ways to look at at generics and at type polymorphism, and we're by far not done with it yet, but this is basically how it's defined. So I want to make this video a bit shorter than before, because this was like a really big change, and also the videos before were kind of long. So the only thing that I'm going to do is I'm going to add yet another method that is going to be as fancy as for each and map, and it goes by the name of flat map. And remember this method, because this method is very, very important in all of programming. If you're a beginner now, believe me that even 10 years from now, you will still learn new things about flat map, right? And flat map, it looks very much the same as map, right? I said this already before, but for each, look at this. I'm gonna copy map like this, duplicate and bring it down, right? It's gonna have pretty much exactly the same signature, but it will take a function that will not produce the result, it will produce a set of results, right? Like that, right? Okay, let's throw an exception over here. We don't have a test for that yet, so everything should still compile. Oh yeah, I should actually rename it like this, flat map. Okay, there we go. Right, so let's go down over here, and let me provide an example of what flat map is actually doing. So I'm gonna call the test for now just flat map, right? And look at the signature. So we are already in a set, and we need a function that produces another set. So we're basically talking about some sort of nesting, right? So the problem that flat map is solving is basically that it's present in nested data structures. And nested data structures, they tend to be dependent on each other, right? It probably doesn't make sense to you. So let me just show you. Imagine, because now we can have sets of whatever we want. Imagine that we have a set of characters instead of strings, right? We have characters, and we're going to have characters like A, B, C. Actually, let me do E, F, G, age like this. And let me see, I can do some sublime magic like this. I can select the commas, I can go right like this, Control D, and do that. Okay, right, so now we have characters, right? And we have another one. Remember, I need to produce some sort of nesting, right? So we have characters and we have numbers, right? So numbers are going to be 1, 2, 3. Scalariform is going to fix this thing for me, 8, right? Okay, so Scalariform injected those spaces for me. Okay, so if I wanted to nest them, the only way to do it now, well, not the only way, but one way to show this nesting would be to use for each. Let's say that we wanted to, our task would be to produce a chessboard. Let's rename the task actually, because now I told you this about chess. Okay, so flat map should be able to produce a chessboard, right? So for now, we're not gonna touch flat map. We're just gonna use print line. So we're gonna have characters for each character, right? And this is where the nesting comes in. So now, instead of working directly with a character, we're going to leave it for a second, and we're going to do for each for numbers. We're going to do numbers for each, right? And this is where the nesting comes from, right? So we have a character and we have a number. So in this scope, we have both of them, right? By the way, remember the video about the cake pattern where we had some nested UIs, and I said that it smells like monoids. Well, basically flat map, like if you ever heard of monoids, of classically arrows, of category theory and all of that stuff, this is the entry point in there. But we're not going to talk about that. All right, so we have this nested data structure, and what we're going to do is we're going to print line a tuple which has a character and the number, right? So we're just going to print it out. So this should print out the chessboard. The order is going to be messed up, obviously, but if I scroll up, see, it produces all of these tuples. The first one is going to be like G and everything for G, right? So we have G7, so we got G1, G2, G3, G4, G5, G6, G7 over here, and G8, right? So we produced everything for G, right? So the G was over here, and then we went through all of the numbers from 1 to 8. Then we did the same thing for E, and we did the same thing for C, and we did the same thing for A, we did the same thing for B, and we did the same thing for D, and so on and so on and so on. So what flat map is doing is it allows us to have this chessboard as a value, right? So we basically can access this thing programmatically, right? So instead of doing that, what we will be able to do is we will be able to have a chessboard, right? Which is going to have a type of a set, right? With a tuple of character and an integer, right? So remember, this is how a chessboard works, right? So there's D1, D2, D3, right? One is a character, the other one is an integer, right? And the way we produce it is by copy pasting that, right? And now we don't need to print out anything. We just need to return the tuple, right? Because this needs to generate a tuple like this, okay? And now let's do it a bit more slowly. So the first one is going to be flat map. It's going to be flat map because this whole situation is for a flat map. The whole idea is that we're going to have flat map that is doing that thing for us. Now, what does flat map need? A flat map needs as a parameter a function that takes an element and produces a set. What function does that? If you think about it, it's map. Map turns has a way of producing something like that, right? If you look at it. So we're going to have flat map over here, and we're going to have map over here. And we're pretty much done, right? So this is a very, very common structure that you have two levels of nesting, right? You have one level of nesting, right? So you have one thing and the other thing, and you have flat map and then map. You're going to see this all the time, especially in functional programming, right? So if we add the implementation, and after that we're going to do chessboard for each print line, then we should see exactly the same thing as over here, right? So let me comment this out, and once we add the implementation and this test is going to become green, we'll actually see this, right? Because as of right now, an exception is being thrown over here, right? So let's implement flat map. Let me do this over here. And let's start here. Now, I'm actually not going to make it so big because I want you to see this over here, because this is basically our solution, right? So somehow we will need to nest for each 2 times over here, right? So that it does this, right? Because we already know that for each produces exactly what we want. We just need to be able to capture that somehow, right? And because we're going to use for each, we're going to do the same trick as always. We're going to have result equals empty result, right? And we're just going to produce a result in the end. And over here, we're going to do for each current equals something, 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 right? As always, right? So in this case, how do we get access to this inner thing, right? the only way that, because current is an element, right? Current is an element, but over here we need to have a nesting. We need to produce somehow a set of elements, right? But we have only one element. And this is one of the beauty about type parametric programming, the term that I just invented, is that if you look at the types and if you do it right, there will be only one possible way to implement it. What is in scope that is just laying around that allows us to convert an element to a set of elements? And it's this, right? It's this function. It just lays around there. So let's just call it function current. Okay. So now we have this, right? But this is another set. So now we can call for each and that, right? We're calling for each and that. And now we're going to call this one outer current. And we're going to call this one inner current. Right? Like this. And what are we going to have in the inner current? Well, basically the very, very similar thing as in map, right? So we're going to have result equals result add. And what are we going to add? Well, we're going to add the inner current. And that's it. That's flat map. So if I scroll up, we should see something like that. Okay. And our test is green, but we're actually not testing anything. So just to save some time, so instead of that, I'm just going to say that chessboard.size should be 64, right? And that's it, because 64, this is how big the chessboard is. Okay. Let me comment this out. Not comment this out. Let me remove actually this comment, right? Okay. So now you sort of have flat map, and I understand that flat map might be a bit complicated. And yeah, you might spend some time trying to understand this. What you might discover is that you actually can implement map with flat map, because flat map is a little bit more powerful than map, right? Actually, let me show you this. So what you can do is, I'm gonna leave this one over here. I'm just gonna copy the signature, bring it down, because we have tests for map. We can just do whatever we want, and then just see that the tests are still going to compile. The test is still going to be green. So I'm going to call this one map old, right? And this is going to be map new, right? So I just said that we can implement map with flat map, right? Because right now map uses for each directly, but because flat map uses for each, well, then maybe map can just use flat map, and then indirectly for each, right? So let's try that. Let's do flat map current. But now we need to produce a set. And we can't produce just a set of elements. We need to produce a set of results. Well, before what we were doing is we were producing a result, right? So we know how to turn an element into a result, right? Let's just call this function. But now we need to convert this into a set. And how do we do this? Well, we just put this element into a set, and that's it. Set. Right? And that's it. Right? So our tests are now calling this instead of that, and it still works, right? So let me just comment this out, just for you to be sure. And there you go. So flat map is basically a more powerful abstraction than map, right? But this is actually not a good idea. Like performance-wise, we're wrapping like every element into a set just to save a few lines of code. That's usually not a good idea. So I'm just going to revert that. I'm going to have a map over here, Going to remove that. Okay. Let me scroll up a little bit and see if I need to change something. But basically I believe that we're done with this video, because I wanted to make it shorter. And in the next video, we're actually going to discover an even more powerful abstraction, and we're going to throw out all of these for eaches and all of these variables. And we're by far not done with generics. In fact, we're going to have some very serious discussions about generics and about those dimensions, how they actually hit on each other like pretty hard, right? So this is actually the real blend of functional programming and object-oriented programming. Remember the video that about the birth of the value proposition of object orientation, where I basically said that the only value that object orientation provides is subtype polymorphism, right? So now we're gonna have we have sort of an alternative, and Scala is a language that blends those two together, and we will see how painful it actually can be once you're programming at this relatively high level, actually. All right. Okay, let me glance at the test for the last time. It should be fine though. There's a for each, there's map, there's flat map, everything is fine. There's an empty line over here. I believe we should be fine. Okay, so let's commit that. Let's go over here, git status. Well, two files changed. We had two files at a time. As you know, I prefer to do git add like this. Let's check git status again. Git commit -am. This is video 4, and this is going to be let's say, I don't want to call it type polymorphism yet. Why not? Let's call it type polymorphism, and let's do /generics. Let's do /map. Let's do /flat map, like this, right? That should be fine. Video 4, blah blah blah. Git push, and there we go. My key is already unlocked. And let's look in the browser. The browser is over here. We have 6 commits now, and we have video 4 over here. And look how much we changed. So basically, you can see exactly like where we added those types. Basically everywhere, almost in every line. It is now everywhere. And then we added map and flat map, so you can take a look at them. And yeah, basically all of this just adds some stuff. Look at the sat suite. We basically fixed a few issues, but basically we didn't change actually much, right? Because type inference helped us out like in most of the cases. All right, that's pretty much it. Like this video if you did. Subscribe if you want to improve the developer inside you. And most importantly, take care.